Alright, in this video we're going to be talking on conformational isomerism of alkanes. Now, conformational isomerism, unlike other forms of isomerism, deals with the position of the substituents in the carbon atom due to the rotation of the carbon atom around a sigma bond in relative space to one another. We can therefore say conformational isomers are structural isomers that can be converted into one another by the rotation of a sigma bond. Now, these definitions that I just gave, they might actually look complex, but when I explain them thoroughly, you might actually get them better. So let's go on. It is mostly exhibited by alkanes. Individual conformational isomers are called conformers. Now, these conformers, they've been existing for a long time, but no one actually knew how to represent them because they were three-dimensional structures, and those days models have not actually 100% been discovered. But now, and you don't really have to be using a model when you're using a textbook. But now, look, in 1955, MS Newman prepared a useful way of drawing the conformation of alkanes in two dimensions. Like I was saying earlier, they were not molecules are represented in three-dimensional structures, but in books, journals, and so on, we can't actually be representing a molecule in three-dimensional structure since we are limited to a two-dimensional structure. So this was actually a problem. So MS Newman actually discovered a useful way of drawing conformation of alkanes in two-dimensional structures. Now, these are called Newman's projection formula. What he actually discovered, they called it Newman's projection formula. And in Newman's projection formula, the carbons are represented by a circle and a dot in the middle of the circle. Now, because we're actually dealing with two carbons lying or overlapping between each other, connected by a sigma bond, the carbons are represented, like I said earlier, one is represented by a circle and the other is represented by dots in the middle of the circle. I'm actually going to show you the projection of this, and I'll use an example to actually describe this. Now, the hydrogen are then drawn projecting from the dot and the circle. Now, something you need to note is that Newman's projection is an end-to-end view of the carbon atoms. Now, what it actually means is that the carbon atoms are found overlapping between each other. So when we're actually viewing one carbon atom, we're actually viewing both carbon atoms because they are overlapping between each other. That's what this actually means. For example, the Newman projection formula for ethane. Now, if I ask you to draw an ethane, you're actually going to draw this. This is all what we know, C2H6. We're actually going to draw this because this is like the two-dimensional structure of ethane. But we all know that this is not how ethane is. If we actually see a model of ethane, it's actually a three-dimensional structure with a carbon overlapping the other carbon, and then they are joined by a sigma bond. And that's what ethane actually looks like, but we can't actually represent it in a two-dimensional board. So MS Newman actually gave us a reasonable way to represent this without actually just a reasonable way to represent this. So let's just go on. Now, I want to label this carbon so it will be easier understood. This is carbon number 1 and carbon number 2. So, carbon number 1, you can actually draw it or represent it by a circle. Like I said earlier, a circle and a dot in the middle of this circle. Now, carbon number 2 will be represented by the dot. Okay. Now we've seen that carbon number 1 has how many hydrogen attached to it? 3 hydrogen atoms attached to it. So let's call this hydrogen 1, hydrogen 2, hydrogen 3. Same thing for carbon number 2. So hydrogen 1, hydrogen 2, and hydrogen 3. Now if we look at this structure, we see that carbon number 1, the carbons are actually touching the circle, and carbon number 2, the carbons are actually touching the line. So that's like how you're meant to be representing it, not just anyhow or in a random way of random pattern. Now, I'm going to be talking on dihedral angle. This angle is so important, but when we're actually going deep into this topic, we're actually going to see the use of this angle and so on. Now, due to the rotation of the carbon atoms around the sigma bond, This leads to the formation of an angle around the substituent. The angle is called the dihedral angle. We can say that the dihedral angle is the angle between the substituents of the carbon atom joined together. Now, when we're actually drawing the circle and the dots, now, like I said, this hydrogen and let me see a hydrogen here. Let's move this here. Let's say they are in the same plane. We can actually see something like this. Take something like this. Hydrogen and hydrogen. Now there's an angle formed between them, and this angle is called the dihedral angle. This angle could be any form of angle. We don't actually know, but unfortunately we're going to see like how they actually group it. Now, types of numerous conformation formulas. There are basically two types of conformers according to numerous conformation system. These are the eclipse or the ciscoid conformer and the staggered or the transitoid conformers. Another name for this staggered or transitoid conformer is the skewed conformer. So, now the eclipse or the ciscoid conformation system. This is a type of numerous conformation formula system in which the angle between the two carbons connected by the sigma bond is as close as possible. So close, the angle that joins the substituent is as close as possible. That means that angle that I'm talking about is the dihedral angle. So let's keep going. This leads to the position of the substituent group to be on the same plane or on a very close plane. According to Newman's projection, when we look at one carbon, the other carbon and the substituent tend to align across the same plane. Just like I said earlier, the carbon will be overlapping. So when we look at one carbon, the other carbon and its substituent, they tend to be aligning on the same plane. And this leads to a dihedral angle of 0 degrees. Now, this is actually like a three-dimensional structure I was actually trying to use to explain. But let me actually explain with Newman's conformation formula system. Now let's use ethane again. Now this is ethane, the normal ethane. This is the normal ethane we all know. But now when we're representing it in Newman's conformation system, we draw our circle and we draw our dots. I'm trying to talk about eclipse or ciscoid conformation system. So this is our first hydrogen. Then we have hydrogen and hydrogen. Now the hydrogen, let me use a different color for the hydrogen of this carbon number 2. Let's just call this one and this 2. So this is hydrogen number 2. Now, do not mind the way this diagram is represented. These two carbons here, they are overlapping between each other. Just as this hydrogen is overlapping, I actually drew them side by side just to show that the two hydrogens are present. But normally we just have to represent it by like one hydrogen because the other hydrogen is at the back of this hydrogen. So according to this structure that we've seen, we will notice that these two hydrogen, they are aligned, they are overlapping between each other. Like I said, in eclipse or ciscoid conformation system, that the hydrogen, the angle between the two carbons connected by the sigma bond is as close as possible. And the close angle that I said before, that's the dihedral angle, it is 0 degrees. Now that's what I'm just representing here. So let's go over to the next form of Newman's conformational isomerism. So let's go. Now this is staggered or the transitoid conformation system. Like I said, it's also called the skewed conformation system. This is a type of Newman's conformation formula in which the angles between the two carbons connected by the sigma bond are as far as possible. This leads to the positioning of the substituent group to be on different plane or as far as possible. Just like in the eclipse or the ciscoid conformation system, the angle was as close as possible. Now this is like the opposite, as far as possible. According to Newman's projection formula, when you look at one carbon atom, the other carbon atom and its substituent are seen at a different plane. And due to the difference in the substituent, like due to the difference in the angle between the substituent, it leads to like the dihedral angle formed between the two substituents, like two opposite substituents, ends up being 60 degrees. Unlike the first one that is 0 degrees, this will be 60 degrees. Now this is like also a 3D representation, but like I said, I'll actually show you how it is done using Newman's projection system. So same example, ethane. Now using Newman's conformation system, a circle first, then the dots. Now these are the hydrogen. Carbon number 1 and carbon number 2. This is the hydrogen of carbon number 2. Now if we look at this, let's consider this. Let's say this hydrogen 1 and this hydrogen 2. Now if we look at this structure, we find out that these two hydrogens, hydrogen 1 and hydrogen 2, they are meant, like unlike Eclipse that they were overlapping each other, these two they are not overlapping. So when you look at an end-to-end view, or you look at it straightforwardly like in the Z plane, we find out that we are able to see these two hydrogen individually, unlike before in Eclipse that we see them, they are mostly like combined together, and as we're looking at one, we are seeing both of them. So now it leads to a dihedral angle of 40. Now I want to like cut this part out and take it and show you. So we have something like this, a hydrogen and a hydrogen, and angle between them is 60 degrees. Now I want you to note something. There are only two types of Newman's projection system, but that doesn't mean that there are two types of conformational system. There are infinite types of conformational system. What I actually mean by that is, let's say we can also have something like this, a hydrogen here, a hydrogen here, a hydrogen here, and now projection a hydrogen here, now a hydrogen here, and now hydrogen here. Now if we look at this, it's another different type of projection. We can have different projection because this sigma bond is actually like, the carbons combined to the sigma bonds are actually rotating. They are rotating. We all know like the characteristic of sigma bond, like they are rotating bonds, like the carbons attached to them, they are rotating. But like pi bonds, they are mobile but they do not rotate, but sigma bonds they rotate. So they are actually rotating, and due to the rotation, the substituent attached, they are constantly changing their position, and that is what conformation is actually talking about. But since we are actually we don't want to like give you infinite possibilities, so we actually gave it into two, that is maximum and minimum, and that's like the two main types of conformers. So let's keep going. Now this staggered conformer that I actually talked about earlier, there are two different types of it also. Now the first one is the trans or anti-staggered conformer, and the second is the gauge conformers. Now these two different types of conformers, they are still under the staggered conformer. They are just different types of conformers under it, and they are mostly found in compounds that contain more than two carbon atoms attached to them. Something like butane, if I use for an example. We all know that when we're talking about Newman's projection, we're only dealing with two carbons, and butane is C4H10. And when we're using Newman's projection, we only have two carbons attached to them. So therefore, the remaining two carbons that are left, they'll end up and they'll turn into the substituent. If I join this in, I can have CH3, CH2, CH2, and CH3. Now, when I'm actually looking at these two hydrogens, these two carbons attached, they'll actually turn to substituent groups of this carbon. of this carbon number one and carbon number two, they actually turn to substituent groups. And when they actually turn to substituent groups, they are not actually like, we don't know what to classify them under, but they are still under staggered conformers. So we now divided staggered conformers into other forms of like conformers, and that is the trans or anti-staggered conformers and the gauge conformers. Now, these types of conformation arise from the presence of methyl substituents, like I said earlier, and it can be found in butane and compounds with further, or what should I say, with further methyl groups attached to them. So let's go further. Now, the trans or anti-staggered conformers. This is a type of staggered conformation system in which the methyl group. Now, look, before we're focusing on like the, what should I say, the normal substituent, that's the hydrogen groups are far away from each other. Now we are no longer focusing on the hydrogen group. We've balanced the hydrogen group. Now, due to the presence of methyl group, we are focusing on the methyl group. Now look at the definition. This is a type of staggered conformation system in which the methyl group present in the carbon atoms are at maximum distance between themselves. Now, this is under staggered conform. Don't get confused. It's still under staggered conformation system. But now under this, we are dealing with the methyl group. So like the normal stuff, let me actually give you the structure of the thing. Now we have C. The structure of the thing, we have C, H. Okay, CH, H, C, H, H, C, H, H, C, H, H, H. And like I said earlier, these two groups here, this and its brother here, they actually turn to become the substituent groups. Now, I'm actually going to release space and remove all these ends, and I'm actually going to show you how to represent it using Newman's projection system. Now, like earlier, it's circle and a dot. Now, from the definition, like I said, they are at maximum distance. The methyl group, they are at maximum distance. So, still like staggered maximum distance. So, let's go. Let's call this CH3, first methyl group. This is the hydrogen, and this is the hydrogen. Now for the second carbon, this is the methyl group. Like I said, they are at maximum distance. The two methyl groups, they are at maximum distance. So for a two methyl group to be at maximum distance, the hydrogen that we see here, since it's always obeying the staggered rule, it will still be at maximum distance. Still obeying the staggered rule. So this hydrogen will still be at maximum distance, but the methyl group personally will be at maximum distance. Now, let's go to the next slide. The gauge staggered conformer. This is a type of staggered conformation system in which the methyl group present in the carbon atom are closer to each other. Now, unlike the trans or the anti-staggered conformation system in which the methyl groups are further away from each other, now this one, they are closer to each other. Now, note something. Trans-staggered conformers are more stable than gauge-staggered conformers. We're actually going to see the stability later on, but let's just go on. Now, like I said, let's use butane for an example. We have something like this. Now, this is my methyl group. Let me use it. Now, let me just reduce the size. This is my methyl group CH3. Now, this is my hydrogen, and this is my hydrogen. Now, like I said here, the methyl groups are present are closer to each other. So, what do we expect? We expect the methyl group to be somewhere here. Oh, this structure is actually so wrong. So let's just draw it again. This is my methyl. Now, like I said earlier, we expect the methyl group to be closer to this other methyl group. They could actually be on the same plane or on a closer plane. Let's just say they are on the same plane, they are overlapping each other. Now, still obeying the rule of staggered isomerism, the two hydrogens here, they are further away from each other. If you understand this, they are not varying, they are still part of staggered isomerism. It's just that the methyl groups are closer to each other. So it's not looking like it's a new form, it's still under staggered because the hydrogen are still further away from each other. Now, like I said earlier, I said in what I put here, trans staggered conformers are more stable than gauge staggered conformers. Now, I'm just going to be talking about the relative stability of all these groups. Now, the first one, now if we look at this, we see that trans or anti-staggered conformers are more stable than gauge conformers, and this is more stable than eclipse conformers. Now, this relative stability is very important. So, like now, if we have like a mixture of all these three conformers in like an organic compound, we can actually decode something. That if we look at this, we know that more trans or anti-staggered conformers will present, more trans will be present than gauge. Let me just say there will be like 60% of trans present. There will be like 30% of gauge present, and there will be like 10% of eclipse present. That's because of the stability of all of these, because we can see that trans is more stable than all of them, than anti-staggered and gauge. So let me just actually give you the final structure of all of this, then we can call this video to a close. Like I said earlier, this is my trans staggered isomers. The methyl group are at further distance between each other. I have my H. Then my CH3. Now this is my first one. This is my trans or anti-staggered isomer or anti-staggered. Yeah, so let's go for the next one. I said it's more stable than. Okay, my hydrogen. Now this is my gauge isomer. Now and this is more stable than eclipse. Eclipse is the least stable. And like I said in this last part, this is actually the structure of all of them. Also, until I give you a final structure and summarize. So, thank you for viewing. Please like and subscribe to my channel. Thank you. Goodbye for now.